I'm Rob Knapp, and I work with Wolfram Research in the numerical computation group, and I'm going to be talking about progress and optimization in the Wolfram language. So mathematical optimization is basically trying to get the best possible value of some function, typically over a set of constraints. But there's lots of categorizations for optimization. It's a really common problem that people want to solve. One categorization is linear versus nonlinear. Another is constrained versus unconstrained. And final one that's very common is local versus global optimization. So global optimum is something for all possible, the best possible value of function within any given set of constraints that you find. Okay, an additional category that's become much more widely used recently, and we've been working on actively in the numerical computation group, is convex optimization. And the big thing about convex optimization is it's nonlinear or sometimes linear, it's constrained, and the optimum you find with convex functions is always global. So convex minimization problem, our optimization problem, is you minimize some convex function f, or to maximize you minimize minus f of x, and you have constraints defined by convex functions g sub I, and possibly linear equality constraints. And so that's something we've worked on pretty hard for the last few versions. And in fact, my slide navigation is not working properly, so I'll have to do this. So in version 12, we added a whole bunch of special cases of convex optimization, from linear optimization through conic optimization. And those are all particular cases of convex optimization. The advantage of these commands is that you're able to get things which is the dual problem out, which actually gives you lots of information about the problem as being solved and sensitivity to constraints and various things like that. In addition, we took n-minimize and find minimum, and we use, in those functions, we use the convex optimization functions automatically when the problem is detected as convex. So part of the code base we have is something that goes through functions and tries to detect when the functions are actually convex and amenable to solution or not. And if it's not, then n-minimize goes back to its old methods, which are typically slower and less reliable. All right, so in version 12.1, we added integer variable support for all of those commands above. And we also added geometric optimization. And this is not a convex problem, but it's actually what's technically called a log convex problem. So it's a special case of log convex optimization. Okay, so now for this version coming up, which we'll call 12.2 for good measure, is things we've just recently added in the last year. And that one is complex variable support. Another is a general command, convex optimization, that sort of subsumes all of those functions before for convenience. Something called parametric convex optimization that allows you to use parameters in your optimization and solve quickly for parameters. I'll show some examples of that. Robust convex optimization. The idea here is you minimize a function, but you want a minimum that's going to be valid for all possible values of some parameter. So it's sort of a different, it and parametric convex optimizations are both themes on a parametric thing. And Paratosh is going to be talking about that in the next half-hour meeting. And we also have a method framework for optimization solvers that include commercial solvers such as Mosaic, Garobi, Express, and Nina's going to be talking about that just after Paratosh. So that's going to be in about an hour. All right, so what's coming in future versions? Well, I'll get to that later. Okay, so let's do a couple examples. And I think that these examples highlight some of the things we're able to do within this convex framework that make it quite convenient. Okay, so I'm going to talk about, so let's minimize a real objective. So that the objective for optimization has to be real. Otherwise, you can't talk about a minimum or maximum because there is no such thing as a minimum or maximum in the complex plane. And then we've got constraints that I've expressed as complex constraints. So let's look at this constraint. Z is greater than I. What does that mean? Well, notice that that's a curvy grader, and that's using this vector grader equal, the inequalities we introduced in version 12. And what this means, for that to be true, it means that both the real and imaginary components both have to be greater at the same time. If they're not both satisfied, it's considered false. So basically that means that the real part of z has to be greater than or equal to 0, and the imaginary part of z has to be greater than or equal to 1. So now we can enter constraints like this, and our standard form gives them in the notation pretty much like I had above. Now let's see how it actually works in the real plane. So suppose z is x plus iy, sort of a standard way of representing a complex number. Okay, and let's do a complex expand on that, and you'll see that I get x. So basically the real parts have to be matched. So basically this means x minus 2y has to be greater than or equal to minus 3, and x has to be greater than or equal to 0, and 2x minus y has to be greater than or equal to 0. So those are the complex constraints. So we can write those as real constraints. So now the region of the complex plane, we can use sort of our implicit region on these real constraints, and it's going to just be a triangle. So I picked a pretty simple problem here. Okay, now we can solve linear optimization on this, and suppose we do real of z. Okay, and if we do the real, it corresponds exactly to doing this linear optimization problem on x. Okay, so we basically, what we do is we internally convert the complex numbers to these reals using some transformations, very much like what I showed you above. It's a bit subtler than that, but not too different. And then we can compute the minimum in the real plane, and then we convert back to complex numbers at the end. So it's sort of an automatic thing. And a lot of convex optimization problems work. Typically, as you get to higher order things, matrices that in other cases have to be symmetric need approximation. Okay, but now here's a slightly simply less example. This looks very like the same difficulty. It's over the same set as before, but now I'm using abs of z2 minus z minus 2i. So we can do that, and it computes the thing immediately. Now it's a little bit hard to see from this, but absolute value of z is it's a function. It's actually the modulus, which is a square root of the real components plus the imaginary components squared. So it's not actually a linear constraint anymore. So this actually has to be solved using convex methods that handle what are called norm cone constraints. And we can go a bit further. And I'm going to take this very simple problem, and I'm going to make it into a parametric convex optimization problem. So much like I did before, okay? But now instead of having some arbitrary particular point I put in, minus 2i, put in z minus theta, and that's going to be my parameter. So my parameter is going to be some point in the complex plane, okay? So for example, I do p fun of 1, and I don't know why these boxes come out. They're normal size outside the slideshow thing. But I can also do p of 2i, okay? And that gives me the minimum I had before. So it can be any point, or I could do p fun of 1 plus 2i. Okay, and we can actually do a quick manipulate that allows me to move around this point in the complex plane. And as I move the point around in the complex plane, and you'll notice that if I pick carefully, I can get to a point in the center, and that's where, and in those cases, this is the actual point I picked in the complex plane, and the minimum is within that set, so it's not at the boundary. So that's a quick example simple example of how you can use parametric convex optimization. All right, so I'm going to take one more example. I'm keeping the number of examples limited so we can sort of explore these commands, these new things, within a limited set of examples rather than throwing too many examples at you. So what I did is I did some timing of matrix multiplication on my machine. So what I did is I timed matrix multiplication, and for each value of n, for each matrix size n, I did 10 different timings, and I collected data from that. And that I've got stored in the note. Rather than making you suffer through waiting for that to come out, I've collected that in advance. And here's a list plot of those timings. So what I'd like to do is I'd like to sort of find, well, what is the approximate complexity of the matrix multiplication within the Wolfram language? Okay, well, this plot makes it pretty hard to see because you see you have huge variation here. So typically with things that you're looking for particularly if you're looking for asymptotic timing, it's better to do it in the log plane. And a quick way to do this that I often use is this function real exponent, which actually just takes a log base 10, but it sort of doesn't worry, it doesn't complain about zeros or negative numbers, it just takes the absolute value. So it's actually more convenient than using log because it avoids singularities. Now notice in this log plane, I can put a plot and actually it looks pretty close to linear. And in fact, the other thing that's useful here is that the variation in the different components is typically comparable. This first one is quite a bit bigger, but the other ones, it's somewhat comparable. So what I want to do is I want to consider this variation as sort of a parametric thing and as an uncertainty, and then do fits based on that view of the data. Okay, so first let's think of doing a linear fit. Well, the way I would normally do a linear fit is, oh, I'm missing something at the bottom of that slide. Well, maybe not. Okay, so yes, I'll get the vector, I'll get some data about the log timing. So I'll call tau bar the means of those timings I have. So the mean for each value of n, and s is the log of the n's I had, okay, which go from 2 to the 8th through 2 to the 12th. And this is going to be the variation. I'll call it delta tau. So the variation in the log space. And I've multiplied this by 3 times the actual variation because I only did 10 realizations. And realistically, I'm probably likely to get more variation, though, you know, the factor I choose is a bit arbitrary. Okay, and here's what the plot looks like. So the variation is showed by the vertical bars, okay, the expanded variation. The gray dots, the gray large dots show where the mean is, and then the other dots are just the plot I showed before, the actual data points. So now let's fit the data. Well, the easy way to fit the data is just use a command fit, right? We don't need to actually do optimization. It's a linear algebra thing. And I get a fit like this, and sort of the translation to an actual model, asymptotic model, is we take 10 to the power of that, and so it's basically some small coefficient times n to the 2.84. Now, of course, we expect that to be 3, but realistically, there's more going on than just the order n cubed of the number of flops going on. There's parallelism, there's how the machine's cache behavior works. So it's much more subtle than the actual mathematical flop complexity, which is what makes it interesting to actually look at this. So now let's look at fitting as optimization. So let's take an objective function, which is, this is going to be the slope of my fit. This is going to be the intercept. These are the points in log n space, okay? This is my tau bar, but I also want to, these are the means, and then I also want to consider an uncertainty delta, which is going to be bound by those uncertainty models I found before. So this is my objective. And I can do a simple, so the simple fit I found before is basically taking the case where delta equals 0. And I can do that with convex optimization. If I just put in a parametric equation, this is what I call a constant parameter equation, it goes ahead and substitutes that in and computes. And that's exactly the fit I got with fit. And it's using roughly similar methods, though the fit is a bit more direct. So now let's consider a robust fit, okay? So let's do this robust fit. Oh, and one other thing I forgot to mention in this is instead of doing convex optimization of the objective, I did convex optimization of R, where objective is less than root R. And this is something you can always do with convex problems, is you can replace some function with some convex function with a new variable, which in this case is R, and the additional constraint that objective is less than or equal to R. And so that's always going to give you the equivalent minimum. So convex optimization can actually always be reduced to the case where you have a linear objective. Now, the reason I use the R here is this actually gives me the residual instantly. So I don't have to go back and compute it later. I have it as a part of my optimization. So it's just very convenient. Now notice here when I do the robust optimization, so this is an optimal value that's valid for all possible values of delta between these uncertainty intervals, that I had. And notice that the optimum seems a lot worse. The residual is worse than the one I did in the simple fit. But it looks worse, but it's not really. So let's look at what's happening here and a different way to look at it. So I've got some functions that are a bit complicated, okay, that sort of compute the worst error. So given a fit and that possible uncertainty, I've defined a function called worst case plot. So let's look at the worst case plot for the robust fit, okay? So basically what I do is the fit value is here, and it computes the farthest I can go in the uncertainty that makes that term in the residual as big as possible, okay? And those are indicated by the red. And so when I do that for the robust fit, I get that residual, which is 0.509, which is exactly what the robust residual had given me. So basically, for any value in the uncertainty, okay, the most the residual is ever going to be is that value, that value given. So if it varies uncertainly, I have this property. Now let's look at the simple fit. Okay, the worst case for the simple fit, we actually get a worse residual. So in cases where the data don't work out properly, you can get a worse residual than the robust fit. And that's the reason to use the robust fit. And Paratosh will show some examples that indicate, you know, if you want to have to order, if you're a manufacturer and you need to order based on some estimate, it's better to make a conservative estimate than risk not making any profit at all. Okay, so let's continue with this problem a bit further. Okay, and let's look at a parametric view of it. So here I'm going to change the objective to get rid of the uncertainty, and I'll just consider the tau, or the timings I got for a particular instance, okay? And I'm going to call it a parametric fit function. So not surprisingly, if I call this parametric fit function with my mean timings, I get exactly that same fit I got before, that simple fit, okay? So I can do a whole bunch of fits, okay, of all the 10 instances of the timing I did, and I get something like this. It's more useful to actually compare, say, to the robust fit. And you see I'm getting within, you know, 0.05 or so, I'm getting slopes and intercepts, which vary quite a bit. Okay, so let's go a bit further with the robust optimization. So let's consider the standard deviation. So let's assume that the timings we get out of the machine, which I think is not an unreasonable assumption, are normally distributed around the means. So let's get a standard deviation. Let's get 1,000 instances of that, okay? And I'll get 1,000 instances using random variate, okay? And then what I'm going to do with that is I'm going to go ahead and fit those, okay? Each of those 1,000 instances. And actually, I think my computers, before this only took like a second, but I think it's because it's doing the talk and everything at once. Okay, so now let's go ahead and look at the envelope of the possible models. Okay, so these are all the possible models from the, this is very similar to before. We've again based it compared to the robust optimization. So you can kind of see the envelope. Something else you can do, which is quite interesting, is you can use the find distribution function to find what is the distribution of these fits. Okay, and it turns out that the slope is normally distributed, or you know, approximately normally distributed with a mean. And you can actually look at the PDF with the histogram in this plot. And so that's the slopes and the intercepts. So it's really very much centered around 2.85. So we can be pretty confident that this slope is not actually 3, but it's something less than that. And again, that makes sense because of the parallelism. Okay, so now let's look at another idea. Which is the sensitivity, okay? So suppose you want to know how the derivative of the fit, and this again, you take the derivative, and because it's a vector parameter, we use this a vector inside the first argument of derivative, so it's not just a prime, it's particularly one particular component of the thing, okay? And we can find the derivative. So basically this says that, you know, if I were to change the first component, okay, the slope changes by, you know, that times delta the first component, and the residual actually decreases as the first component increases, which makes sense, okay? Now, something else you want to be able to do, and this is a view into the future, is we're going to eventually have a design that allow you to get all of these, the gradient with respect to all of these parameters at once. So here I'm taking, this is in the function space, so this would be the third component of the function, which is the residual. And so if I do this, this gives me the gradient of the residual with respect to all the parameters at once. And so notice this matches this. And for interest of time, I don't have more to go into this, but this will actually tie into automatic differentiation that we'll eventually have in the compiler as well. Okay, so now it's time to talk about future plans. Okay, so this is a mistake. I should have gotten rid of that. But okay, so things we're going to work on in the future is stochastic optimization. And actually that example I showed you where I got the distribution is an example of stochastic optimization. We'll actually mathematically be able to get the distributions properly. And there's a few different techniques in that. Another is multi-objective optimization. So what if you have trade-offs between, so do two different things and you want to sort of weigh those. We get, optimal values along what's the so-called Pareto front. And then the next thing we're going to start working on is global nonlinear optimization. There's all sorts of techniques. Now, general global nonlinear optimization, we have in find minimum and minimize. It sort of works, but it often runs into problem, and that many of you have found. So what we're going to try and do is use some particular techniques that show great promise, and we can actually get really good solutions for. And we're going to try and classify problems as much as possible using the symbolic part of the Wolfram engine. Okay, so one is quasi-convex optimization. This is just an extension of convex optimization, and linear fractional programming is an example. And then we'll extend the log convex optimization to be more general. We'll have what's called difference of convex optimization. So that's a convex function minus plus a concave function, which is, or a convex function minus some other convex function. And all twice differentiable functions are in this class. We're going to set up a framework for branch and bound, a general framework that will allow us to do things like using convex approximations and using envelope calculations on that. And then we'll have stochastic methods. That's kind of like the random search and minimize, but it'll have much improved efficiencies. Because it'll use some of these faster methods on the line. We'll also eventually do some statistical problem classes. One we're sort of starting to look at now is, say, packing problems. How do you pack pallets into an airplane? Or how do you do floor design to pack things in? So those are things coming in the near future. I mean, the long-term future will eventually have sort of n minimize and find minimum really souped up to work very efficiently in a huge number of cases. So to kind of conclude, I'm going to do this. So I'm going to show you one more example with convex optimization. And so I'm going to take an image, which is corrupted, that I showed in my original title slot. It actually looks like this. And the idea is what you do is if I've got a bunch of pixels that have been kind of zeroed out, and I want to sort of restore the image as much as possible. Well, a way to do that is to minimize this total variation, which is a sum of norms of each component, each pixel with its nearby pixels. So you minimize that, okay? And then, so a trick for actually doing this efficiently is to use the sparse array of the data. And this is a quick way to find zeros. And I want to keep all the pixels that weren't zeroed at their original values, okay? Then I set up constraints, which are the variations. And I'm doing this with conic optimization, one of our solvers. And this takes a bit of time. And I'll go ahead and enter this, and eventually it will show up. But in the meantime, you can ask any questions that you may have. You can start asking questions now. Now let me see if I can find my chat. I'm going to minimize this. And there was one question in the chat. Oh, this is not. Maybe because my computer is bogged down computing this, because this is a fairly large minimization problem. But one question that was asked in the chat for the pathable thing was, You know, could we add a performance goal to n minimize? And actually, I think that's a really good idea. So it finally did this, and if you see, we got a corrected image. So the answer to the question is, you know, can we add a performance goal to find and minimize? And the answer is yes, we'll do that. We may not do this for this next version, but we should have something fairly soon. And in fact, all of these convex optimization functions we've put together do have a performance goal, and they kind of do a trade-off between tolerance and the automatic tolerance. And I think that's a really good idea for n minimize. So we'll have that before too long. So let's see. So there's a whole bunch of questions. I'll look at that. Okay, so yes, I'll figure out, somebody will tell me how to add the notebook and I'll add it somehow. That's past my level of technology. But Michael, your question was the residual given earlier defined or just a free variable? So the residual, as I showed in that, as an objective R, was a free variable that I added, but it's going to, when it finds the optimum, it's going to be equal to that minimum value of the objective. I don't know if that completely answers your question. And then, is there a general class of functions that can be transformed into convex problems? Well, the answer is yes, but it's not going to be very satisfying. Convex functions can be transformed into convex problems. And what for the general nonlinear case that we're considering is functions that can be approximated closely by convex functions. That's where we'll look into the branch and bound methods, that we get a convex envelope approximation, and then we see how good that is by using a branch and bound framework to find that. Okay, I think we're good. I think we're actually out of time now. So thank you for your attention.